Merci, donc bonjour à tout le monde et c'est un plaisir d'être là. Je tiens à remercier Camille et Dominique pour l'invitation. Donc je m'excuse parce que je suis un peu malade, donc ça va pas être facile. Plus les Français n'étant pas ma langue maternelle, je me sens pas très à l'aise de faire une présentation scientifique en français. Donc ça va très bien pour discuter, pour aller manger, boire un pot, mais pour les présentations scientifiques, vraiment, je ne ris pas. Donc, je vous demande excuse et puis j'aimerais faire ça en anglais, si c'est acceptable. Et puis, évidemment, pour les questions, il n'y a absolument aucun problème. C'est un plaisir de répondre en français. Donc, so what I would like to share with you is some of our recent work on done on milk protein in particular, and how this can be reshaped into protein fibrils. And hopefully I'll try to convince you how you can use combined scattering and microscopy techniques to get insight into the systems from both a very fundamental and also applied point of view. So structure, properties, and also function on this system. So our favorite protein is beta-lactoglobulin. This is our favorite protein for a number of reasons. First of all, it's very inexpensive. This is the most common globular protein you find in milk. It's also very cheap for the same reason, and it's a model system. So you can get it in a very high purity. You see this is a 4 nanometer in the native states, as a very accessible isoelectric point. So we do understand very well the properties of this protein in the native state. But what we are mostly interested in is actually what happened when you unfold the protein. Okay, so here I'm showing you 3 different possible shapes. If you keep this protein unfolding for like 4 or 5 hours at 80 degrees, depending on a number of factors, so pH, but also ionic strength, you can either get fibrils, as in this case you can get spherical-like micelles, and you can get these fractal worm-like aggregates, which are slightly branched. So of course you can extract the same information by scattering techniques. What I'm showing you here is consistent with the microscopy images. In the case of the worm-like aggregate, you get a fractal exponent that you would like to see. These spherical aggregates, they have a sharp interface, a porrod-like behavior, but inside they have a microgel behavior, so they have a change in the slope. And I like to bring your attention on the fibers, because this is the thing I'm going to talk about in the end. You see that this is the perfect signature of a semi-flexible polymer. So in the in the high angle, you see that you can probe the cross-section. If you go intermediate angle, you see the Q-1. It's just telling you that these objects are rigid. And if you go a very low angle, you get a flexible behavior. So this is actually the signature you will expect for any semi-flexible polymer or polyelectrolyte, with one major difference. Here we use 1, 2, 3, 4, nearly 5 decades in the scattering vector. So we have to use here in the high Q is small angle neutron scattering. This is small angle light scattering, and at the very low Q we use ultra small angle light scattering. So in order to probe all the different fractal regimes, we have to come up with different scattering techniques together. So the message is that they do behave as polymers, but at length scales which are a few order magnitude larger. Now, of course, this gives you insight on the collective behavior, but if you want to understand how these fibers look like at a much smaller length scale, you can only not rely on scattering techniques. So from this understanding to the next slide, we actually spent a few years, and I'm just showing you the final result of several years' work. What you see here is a coarse-grained molecular dynamic reconstruction of these fibers at the resolution of a single protofilament. So this protofilament is about 2 nanometers. And what you see is that the fibers are formed by different protofilaments coming together and twisting for a number of reasons which depend on the electrostatic repulsion, elastic energy along the fibers, and chirality, because all these fibers are all left-ended. So the way we got here is just to apply systematically atomic force microscopy, understand how the persistent length, the height is scaling with different cross-section, and so on. So this is actually very long work. This is a bit the summary of this work. You see, these are the AFM images, and we can reconstruct in each case the structure of the fibrils. So this is a very rich polymorphism. In this case, so if you keep the beta-lactoglobulin unfolding and aggregating for 5 hours, you get up to 5 protofilament coming together and twisting. So you see that the pitch is actually, the period is increasing with the number of filaments. So it was quite an effort to get to this point. So this is what you get if you do everything for 5 hours, 80 degrees. But you can keep the reaction running for a longer time. And then what you get is you just promote more and more the lateral aggregation of the fiber. So here you can see the individual protofilament resolved by atomic force microscopy. We can count up to 16 protofilaments. And the reason why now here they appear so evident is because you go from a twisted ribbon to an helical ribbon. Helical ribbon has a very low, it has a high mean curvature, so you can smash it down to the substrate, but it has no Gaussian curvature, so it has no twisting. That's why you can resolve the individual filament much better. And the reason for this behavior is that nature has invested millions of years to fold properly the protein. So as soon as you unfold it and you hydrolyze, because we do that at pH 2, what you do is that you expose against water those segments, those residues, which nature took millions of years to fold it in the middle of the protein. So you promote the hydrophobic interaction, and the result is fibrillation and lateral aggregation. Okay, so this is for beta-lactoglobulin. This is actually general behavior. I'm showing you here lysozyme. So we go from milk to egg proteins. You see, same story here. We can resolve up to 17 protofilaments. So if you unfold and hydrolyze any native protein, you get into this highly laminated fibrilla structure. So we really think this is a general behavior, and again what brings things together is the hydrophobic interaction, but of course you need to first align the protofilament. And I like these slides a lot because this shows you all what you see here is still individual protofilament. There is no periodicity along the protofilament, but you see that they have started to align and attach at some specific points. If this is only at the early time, if you wait hours, you see that they start to attach over all the contour length and twist to get the final shape I just showed you. So I'm showing you this slide just to convince you that liquid crystalline interaction are important to align the different protofilaments. And in fact, if you look at the phase diagram of this system, it doesn't come as a surprise that the nematic phase, the aligned phase of the fibers is dominating the phase diagram. So if you are below 0.5%, you are still an isotropic fluid, but just above 0.5%, you have a nematic phase, which doesn't change much if you change the pH. Of course, if you go now to a pH which is very close to the isoelectric point of the protein, the linear charge density on the fibers is not enough to keep things together, and you start to have aggregation in this region. But again, far from this pH, you do see again isotropic and nematic, isotropic and nematic. Of course, if you start to go at 5% or beyond, the systems start to percolate and you get into a gel region. So this is a colloidal behavior which we understand pretty well. You can rationalize the isotropic nematic transition with Onsager theory, for instance, and you just have to readapt that to account. So you have, this is just a theory which is based on a beautiful paper of Lars Onsager in 1949, if I'm not wrong. And this base is a purely entropic consideration. So it's based on excluded volume. And if at the critical excluded volume, fibers do polarize into a nematic phase, and if you do things correctly, considering the excluded volume, you see that the onset of isotropic nematic transition is observed at the critical value, which depends only on the shape of the system. Okay, so this is the diameter, this is an effective diameter, and this is the contour length. So the highest is this ratio. The earlier you will see the nematic phase appearing. You have to correct for a few things. First of all, the fibers are heavily charged, so you have to take the physical diameter plus the double ions layer. So this is the Debye length, which is multiplying an object which is a function of the linear charge density. So if you have a very high salinity, the effective diameter goes back to the original diameter, because this gets very small, or if you change the pH, this also gets very small. And the other correction you have to do is that only that portion of the fiber which is actually rigid contribute to liquid crystalline behavior. So you have to replace the contour length with the persistent length. And if you do that, this is the experimental points. This is the theoretical onset. You see that there is a delay, for instance, with ionic strength, because you're getting the effective diameter smaller and smaller, and within 0.1%, the theory does a pretty good job to capture this first order thermodynamic transition. Of course, you can go back to scattering again, and you can learn a number of other things. What I'm showing here is static light scattering. The thing is that you need to, if you want to have access to the thermodynamic, you have to extrapolate the value of the scattering at very low angle. To do that, we've used a prism, which is an integral theory where you can fit these scattering lines if you have an appropriate closing relationship for the energy. The energy here is contains two terms. One is the excluded volume, which is nothing else than counting the contact between the fibers. So you see is inversely proportional to the length, it's proportional to the density of the fiber. And the other one is the orientation. So this is the order parameter that you can extract, for instance, from either light or neutron scattering data. And I'll show you in a few minutes a slide where you can do that. So if you do that, you can extrapolate this curve. Now, if you go at very low Q, you enter into the Guinier regime. You can get the inverse of the intercept, which is nothing else than the osmotic compressibility. And if you now plot the osmotic compressibility versus concentration, the slope is the second virial coefficient. It tells you a lot about interactions between the different fibers. And in fact, so these are the values you get from the extrapolation, and you see, you do expect that the isotropic nematic transition, you have a change in the second virial coefficient. You have to minimize interaction, and in fact, you see that the slope changes, and it changes exactly 0.3%. So this is exactly the expected concentration at which the second virial coefficient changes in accordance with this phase transition. So this is what happens naturally, because to minimize energy, the system wants to minimize orientation, but you can control that if you start to use external fields. You can do that in a number of ways. Of course, you can shear the system. I just want to show you one case again to illustrate how neutron scattering can provide valuable information. So what we've been doing here is just to mix the fibril with magnetic nanoparticle. This is iron oxide. Of course, now you can do that either with the cluster I was telling you in the beginning or the fiber. So I just want to bring your attention to the fiber case. You apply a magnetic field, you expect to have an alignment, and this is precisely what happens. So this is 0 Tesla, so everything looks isotropic. These are, again, small angle neutron scattering data collected at PSI, and when you start to increase the magnetic field, you see the profile gets anisotropic, 1 Tesla, 5 Tesla, it gets more and more isotropic. This is the azimuthal integration. You said you go from a fully isotropic system to a highly anisotropic. So of course we've been doing that at very low content of fiber to be in the as close as possible to the isotropic phase. And from that you can actually extract the order parameter, which I showed you in the previous slide, can be useful to look into the osmotic compressibility of the system. So just to convince you that you can use microscopy and scattering also to look into application of this system. And before I go into a few possible applications, I want to bring up two other things. First of all, these fibers, again, as polymers are, they are semi-flexible. So I show you this information is accessible through small angle neutron scattering. You see a change in the fractal exponent. But if you do microscopy, it's just exactly the same thing, but you do everything in 2D. So this is the end-to-end distance. So these are a polymer, in fact. This is the particle, the coordinates trace on the AFM or TEM. This is the end-to-end distance, so it's the distance between any points and another point versus the contour length. So this is in fact the end-to-end distance versus the molecular weight of the polymer. And you see below the persistent length, everything is straight, so the end-to-end distance is identical to the contour length. You have 1 as a fractal exponent, and if you go beyond the persistent length, you get 3/4, okay? 0.75. And for those of you who are familiar with polymer physics, 3/4 is the characteristic exponent of a self-avoiding random walk in 2 dimensions. Is the thing, the exponent which comes out from the Flory argument. So this is for lysozyme. It's a general thing. I'm showing you here bovine serum albumin. Again, okay, this is a log scale. This is a log of the contour length. You see one slope here. You see another slope here. And if you work out the fractal exponent, this is how the fractal exponent is evolving. You see, if the system is long enough, you go back to 0.75, and the way you go that is really with a plateau, which tells you that you really have reached self-similarity. So this system really behaves like polymer, like any other polymer would behave on 2 dimensions. So this is the first thing I want to bring up. The other thing is that the system is, these fibers are really rigid. Now, if you know how the persistent length goes with the cross-section, just to remind you, the persistent length is the Young modulus times the cross-area moment of inertia over kBt. So you know how the cross-area moment of inertia is just a geometrical consideration go for a given cross-section. So the only thing which is left over is the Young modulus, and by linear extrapolation you can get that. We get around 5 gigapascal, and in fact, if you measure directly the modulus by non-indentation, you get a value which is very close, okay? So when you talk about gigapascal, this is very rigid. It's not as rigid as cellulose, but it's very rigid to look into a number of possible applications. You have now an object which comes as a native protein from milk. You can reshape it into fibers. These fibers are very rigid, as you see here, are semi-flexible. So you can use this system as you will do a lot of things with polymer. So we have been working on a number of applications on that. And unfortunately, I don't have too much time to go through that, but we have been using these fibers from optoelectronics to health or biosensors, food application, and so on. I want to bring up with you two applications. The first one was inspired by a work by my good friend Harjinder Singh in New Zealand, which was looking at these fibers, again, from beta-lactoglobulin, how these are digested in the stomach, okay? And the way they did that is they will they will do in vitro digestion with pepsin, with a gastric fluid, see how the contour length change with time. They have to do a lot of TEM, look at the contour length evolution with time at this pH. So, but this proves in the end that these fibers are digested. And we wanted to do something in one shot to measure the effect of digestion on the system. So we used the fiber to design some very simple biosensor. You know, graphene is very trendy these days, so we use graphene because it's a one single molecular sheet which is highly conductive. So we mix these fibers with graphene in a suspension. This is actually graphene oxide, which is reduced to graphene. And then we have flakes of graphene, which are stabilized by the fibril, and we can filter that. This is exactly the same technology you use to generate common paper. Okay, paper technology does the same story, but use cellulose fibers. So this is the same story. We generate this system. Now I just want to show you the steps. So this is 1 part of graphene for 8 parts by weight of protein. This is cryo-TEM. You see that the fibers are absorbed on the shell of the on the surface of the graphene. This is the same story with the AFM, but in the end, when you filter, you can get that like a paper which is black because of the graphene, but this is the way it looks like, and you can control the thickness just based with how much of the protein and the graphene you put in the suspension. Now this object here is something which is made by protein and graphene, where graphene is conductive, okay? So in principle, you can close a circuit, and you will expect that well, you know, I mean, if you expose it to the enzyme, the properties of the film have to change. So biologists, they measure the enzyme activity as the number of substrate converted over a given time. And in this case, we said if this is going to work, the change of the conversion of the substrate, which is our fibers in this case, has to be reflected by a change in the resistance of the system. And now what we do is, just because we are physicists, we want to work with you know, with rescaled things, so we just normalize that, and this is now an effective, is the same story, but is normalized. So this is now the enzyme activity is defined to be between 0 and 1. If you have an enzyme which is extremely aggressive, it comes and it opens the circuit, this goes instantaneously to infinite. So the enzyme activity is 1. If the enzyme is poorly inactive, this is always equal to R0. So this is 1 minus 1 is 0. So the enzyme activity is defined to be between 0 and 1. And in fact, it works very well. This is the pepsin. You see the activity with the observation time, it goes up. And in the case of pepsin properly folded, if you unfold pepsin either with alcohol or with temperature, so it's not native any longer, you see that this has lost nearly entirely the activity. So that's one example. Here we're dealing with food in this conference, so I want to show you that these fibers are extremely efficient to stabilize interfaces, which is one of the major goals in food. And how do I convince you on that? Well, first of all, they are very efficient in dropping the surface tension. As you can see here, these are different type of fibers, but these are the native monomers. You see that the fibers do a much better job in the surface tension. This is the interfacial shear moduli. You see these are again the native monomer, and you see within 1 hour or something you have gained order of magnitude in the stiffness, in the rigidity of the interface. So if you want to kill or stop coalescence or disproportionation in emulsion, you want to decrease the ratio between the surface tension and the extensional Young modulus. Right, so this has a ratio which has to be less than a half. So this is the shear modulus, but this is the same story. It's decreasing the surface tension, it's increasing the Young modulus, so it's very efficient to stabilize interfaces. So you can use it for stabilizing emulsion, foams, and so on. And of course, we wanted to know what is going on at the interface, so one good way to look into that is to follow the trajectory of fluorescent particle at the air-water interface during absorption of the fibers from the water phase, and to follow these traces. So this is a technique which can give you a lot of very valuable information. I tried to summarize them in this slide. First of all, you can distinguish between particles which are at the interface, which are the bright particle here, and the one which is dimmer are the one which are flying swimming happily in bulk. So the red traces are those of the particles swimming in bulk with a very low concentration of fibers. You see they follow a perfectly Brownian motion. This is the mean square displacement in 2D versus time. The slope is 1. They are fully isotropic. But the particle on the interface, they have a 1D hopping motion, okay, and they are strongly subdiffusive. So this is in line with the fact that we do know already that the interfaces are viscoelastic. But the new piece of information is that there is a 1D hopping motion. And if you try to correlate the trajectory of all the particles, you see that the 2D order parameter is very high. So this is telling you that all the traces are moving in the nematic islands. And you can obviously map the interface. You have region where they are, the trajectory are strongly aligned, and the region where they're strongly isotropic. So when we got to this point, I got really interested because of two reasons. First of all, if you see isotropic and nematic coexistence in 2D, this will suggest that this is a first order transition. And this is debated over now more than 30 years whether the isotropic nematic transition in 2 dimensions is a first or second order transition. So this will suggest that this is a first order transition. And the other reason why I got really interested is that isotropic nematic transition in 2 dimensions is actually an ubiquitous phenomenon. It's much more common than you can think. And I want to show you where you can get the isotropic nematic transition in 2D at a much larger length scale. This is the way they harvest timber in North American forests through rivers. And you see clearly you have isotropic nematic transition with different nematic grains on the surface. So we wanted to look into that more in detail, and the way to do that is to compare the particle traces that you get from fluorescence with other technique. So this is, we develop a new technique, is a modified Langmuir-Schäfer, where you pick up the interface without an angle. Okay, so it's not Langmuir-Blodgett where you have a contact angle. You just go horizontally and you pick up the interface, and this is again detail without any artifact. And we do know that this is without any artifact because if you cross-check with the third technique, which is cryo-SCM, and you peel off the oil phase, you see everything from the oil phase into the water phase, you do see again in all these techniques isotropic and nematic phases are coexisting in 2D. So is this enough to say that this is a first order transition? And of course, images like this one, they give you a lot of information. And of course, if you try to work out an order parameter, this is as a box size dependence. Okay, so there is an evolution of the 2D order parameter. And if you do that correctly, actually, this is quite non-trivial to work out, because when you look into the dependence of the order with the size, there are two components. One is from the truly nematic phase in 2D. But the other thing is from the isotropic phase, because an isotropic phase has truly zero order parameter only if you have an infinite box size. Even if you have random order, if you make it smaller and smaller, the box size, you increase the apparent order parameter. And in fact, one single fiber has order parameter 1. So you have to take out this background from what you observe, and then you work out the real evolution of the 2D order parameter. And now you can weigh that with the two components, the nematic phase and the isotropic phase. So in this case, 52% is nematic and 48% will be isotropic. Then you can redesign the experiment in a slightly more controlled way. So you can, this is the interfacial density. And you can measure things when you have reached the same interfacial density, as in this case, but starting from a bulk solution which is either high in concentration or low in concentration. So either you put a lot of protein fibers in water, or you put very little amount of protein fibers in water. And in one case you get the large nematic coverage, in the other case you get a low nematic coverage. But now guess which one of the two is the one which starts from the high bulk concentration. I will guess this is the one, but it's exactly the other way around. The high nematic coverage is obtained when you have a very dilute bulk solution. You just have to wait long enough to go to the same coverage. If you do things very fast, at that coverage from a very dense very dense bulk phase, you get a very low coverage. So what happens here is that the system needs time to get the fibers oriented into D, because these fibers are very long and they have a huge excluded volume. So if you give them time, they order. If you don't give them time, they just get stuck into a very disordered thing. And now we do understand why the isotropic nematic transition into D is debated by more than 30 years, because non-equilibrium, this is the signature of non-equilibrium phenomenon. So non-equilibrium phenomenon do dominate this kind of behavior. So observing isotropic and nematic coexisting into D is not something which allows you unambiguously to say whether this is a first or second order transition. So I'm running out of time, so I just want to acknowledge a lot of people. So half of my group is involved with amyloid fibers, so that I will not go through all of them, but this is a really major activity in our group. This is the group I said, look, about just slightly more than a year ago. And with this, I'd like to thank you for your attention, and please don't be shy, ask questions. En français.
J'ai une question, Raphaëlle.
Oui.
Ce que tu nous as présenté, en fait, c'est beaucoup de choses sont parties à partir de bêta-lactoglobuline, lysozyme, oui. Donc des protéines pures. Si maintenant, est-ce que vous avez fait des mesures de formation de fibrilles à partir de whey protein? C'est-à-dire en présence, par exemple, de sel?
Oui. Alors, nous, on n'a pas fait, mais c'est connu. On peut faire... il y a d'autres groupes, par exemple en Nouvelle-Zélande, qui travaillent beaucoup sur les whey protein isolate. Et ça, c'est à peu près la même chose. La conformation des fibres, elle est légèrement différente, mais on forme des fibres dans les mêmes conditions. Donc, c'est tout à fait général, en fait.
Et c'est utilisé après pour des applications de capteurs, ou ça, tu as connaissance de ça aussi? C'est-à-dire d'aller aussi loin que de former des capteurs?
Donc, c'est utilisé, ça commence à être utilisé pour plusieurs applications. Donc, pour tout ce qui est alimentaire, il y a encore une barrière parce que la protéine elle n'est plus dans l'état natif, donc elle est hydrolysée et forme ce qu'on associe aux fibres amyloïdales qui sont associées à tous les neurodegenerative disease, etc. Mais donc, d'après notre évidence et l'évidence aussi du groupe de Singh, ces protéines sont digérées, donc ils sont tout à fait... il n'y a pas d'effet toxique. On a aussi fait des études de cytotoxicity dans plusieurs familles de cellules différentes. On ne voit jamais ni des cytotoxicité ni d'activation. Donc, en principe, la voie est ouverte pour des applications très variées, qui soient alimentaires, mais qui soient aussi biomatériaux.
Okay. Et deuxième question, justement, par rapport à la digestibilité, la bêta-lactogluline est reconnue comme l'une des protéines responsables des allergies. Et c'est souvent associé, et c'est associé au fait que justement cette protéine ne soit pas digestible. Donc le fait finalement de la dénaturer la rendrait plus digestible.
Oui, alors donc effectivement, ça c'est justement la... donc je n'ai pas de réponse définitive à ça, mais mon impression c'est oui, parce que comme je disais au départ, effectivement... La protéine native, elle est très résistante aux enzymes. Donc, c'est une des raisons pour pouvoir l'ergogène très élevé. Là, c'est hydrolysé. Donc, je suppose que cela doit faciliter en tout cas la digestion. Et aussi, ma fille, elle était allergique aux protéines du lait. Ben, la solution, c'était de soigner ça avec des protéines hydrolysées, des soja, mais hydrolysées. Donc, tout ce qui est hydrolysé, ça favorise la digestion.